Hello, I'm David. I'm the coordinator of the Maths Learning Centre. Mostly people know that already, but if you're watching this in the future, hello from the past. I hope it's nicer there because we've been having a tough time here in 2020, 2021. So hello. This is a revision seminar for Stats and Numerical Methods II. And we're still figuring out what we want to actually study. But I was just going to say on the recording that a useful way of dealing with not being able to take your own notes is to attach your memory to the notes that you will have. And so I found that having a piece of paper that has the notes that they have in the middle of it and writing extra things around it, so that even if I can't take that with me into my exam, like to my computer when I'm doing my profit exam or into the physical exam, I can imagine the larger sheet that the sheet they've given me and imagine the arrows that connected things to it. It doesn't work for everybody, but my memory works spatially. I remember where I am in space and I don't have pictures in my head at all, but I can remember if I knew that I had a note at this spot on the formula sheet that they give me, I can look at the formula sheet they give me and go, there was a note in this spot, what was that? Oh yes, that's right, this only works for regression or whatever. So that's just one strategy that may help you. Because unfortunately, every exam is a new experience that you have to learn how to do that kind of exam. So yeah, I'm going to pause the recording for a bit. If you're watching us in the future, you won't notice a difference, but I'm just going to pause it while we're figuring out what we're going to talk about. All right, what we're going to talk about first is some statistics stuff. And the request I've had is about ChiSquared tests in particular, but also just what kinds of tests there are and how they go. And also, how do you talk about some of these things without being wrong, even though you seemed like it was reasonable? So I'll do what I can. And then we'll try and get to the numerical methods later. And I can go over time if I want to, because there's not one after this. Yeah. Okay. Right. Okay, let me have a quick flick through your notes. This bit of the note seems to say that we have 1, 2, 3, 4, 5, 6, 7, 8 hypothesis tests up to this page 82 / confidence intervals. And then after this, we have goodness of fit, tests for independence, and linear regression, which has its own tests in it. And then that feels like it's the end of stats, right? And now we're into interpolating, and so that's numerical methods. Okay, so just checking, the phrase multiple regression doesn't seem to have come up. Good. Okay, sweet. This is your seminar. Please interrupt me if I've made a mistake. You do not have to wait for me to finish the sentence. If I've written a minus where it's supposed to be a plus or vice versa, stop me right then and tell me. If you want to ask a question about something I've said, then wait to the end of the sentence and ask. If you have a question that is sort of vaguely related and you just want it to be used, want it to be aired at some point, that's fine. I'll just say I'll answer that later. It's your thing. So that goes for you in the Zoom as well. Feel free to just turn on your mic and call out, or stick up your hand thingy, but calling out will be more productive. I just want you to know that you can stop me at any point. It's your seminar. It's about your understanding and you feeling like you can do this exam. Yeah, I can talk about this all day long, but it's, you know, that would be just me. So yeah, I will try and stop about every 5 to 10 minutes to give you that opportunity. So yeah. All right, let's just have a talk about the stats. Okay, so was there probability in this as well? Okay, I'm not going to talk about that yet. If you want me to talk about it, we can fit it in, but people have been specifically worried about the stats procedures at the moment and not the probability. But we can get back to that another time. But I want to talk about these procedures that go around this ChiSquared test. So I'm just going to talk about it my own way. It will hopefully line up with some of the things your lecturer says. Yeah. If it seems different, then let me know and I'll try and match them up. The purpose of statistics is to deal with the fact that there is variation in the world. The variation causes a need for stats. If every time you did an experiment on your prototype robot arm, the same thing happened every time, you would only have to do it once. But that's just not how the world works. There is always random crap that you haven't thought of and random crap you can't think of. And so we need a way of dealing with that, and randomness is how we deal with model variation as mathematicians. And statistics is a way of leveraging that, what we know about randomness, to help make decisions even though there's variation. I'm not going to say make decisions. I'm going to help to answer questions in a world where there's variations. So it helps to answer questions using data. Statistics is only good at some kinds of questions, and it will only work if you have data. The type of data you have dictates the sort of statistics that you can do. And the type of question you're asking dictates the sort of statistics that you need to do. So some data, you're not capable of calculating certain things. So if all you have is a list of yeses and nos, you can't calculate an average because they're just words. But you can calculate a percentage of how many yeses there are. Or if you like, proportion, which is what your lecturer calls it in stats. But if you've got numbers, you can average them. And so you can do more things with numbers with data that is numbers than data that is words. And there's different kinds of questions you can answer. The most ultimate kind of question that statistics is usually trying to answer is to predict something. Or possibly explain. They're really the same thing, though don't talk to the writing center coordinator. He's a philosopher and he will not agree with you. Predict is using information from the now to see what's going to happen in the future. Explain is using information from the past to try and figure out what's going on now. And so they're really the same thing. But that's the ultimate question, really, that you're really in almost all forms of science and engineering that you're aiming for. If I do these things, what will happen? And if I do these things instead, will it be better? I mean, ultimately, that's the goal. We don't want to just understand variation. We want to control it. We want to go, these things are different. We would prefer them to not be so different because our machine that we built would be better if it wasn't different all the time. So that's the idea. All right, but there are other questions that you can ask as well. Statistics is only capable of answering extremely specific questions. Okay, so predict or explain. Questions of a predict or explain nature is what regression is for. So the ultimate goal of regression is to predict. To say, I noticed that there was a graph, I thought it was actually useful. I noticed that the amount of sleep a student gets per week seems to be related to their grade. How is that related? Can I, from the amount of sleep do a calculation to predict what their grade might be, or at least to within a certain amount? Can I predict how much an extra sleep hour of sleep per day will have on their grade? That's the sort of thing that regression is for. But you may just have some simpler questions which are less ultimate than that, and you need to ask along the way. So there are three other main kinds of questions that statistics answers. There is yes or no questions. And yes or no questions are what hypothesis tests and p-values are for. If you see a p-value, there is a yes or no question that p-value is attempting to help you answer. Every p-value goes with a yes or no question. It's just a really useful thing to hold on to. And there is a what's the number? That is what confidence intervals are for. Now, confidence intervals and hypothesis tests go together because often your yes or no question is about a number. So you might say, what is the mean amount of expansion that this thing undergoes when it's heated? That's a what's this number question. But the question of, is that amount of expansion greater than, you know, 0.5 millimeter, which is all I've got to be able to have it still fit inside the thing it's supposed to fit in? That's a yes or no question. It's a yes or no question about a number, but it's still a yes or no question. And so you tend to use the same data to answer these questions. So they tend to go together. And then the least specific kind of question is like, what the hell is going on? What's going on? Which is a general question, and statistics is not particularly good at it. And if all you have is a what's going on question, then what you're doing is called descriptive statistics. And descriptive statistics means, you know, graphs or graphs if you prefer. My children just always go on about me about how I say graphs wrong. But I was born in New South Wales, so. Descriptive statistics, graphs, and like just the basic numbers, like just straight up calculating a mean. Means, proportions. So when your lecturer says to you, make a scatter plot, what do you observe? That's a what's going on question. It's not specific enough to be any of these things. And so you'll say, oh, well, it seems like there's a strong positive relationship between these things. That's descriptive statistics. But if they ask, you know, do a hypothesis test to find out if there's a relationship between these things. Oh, if there's a relationship, that's a yes or no question. Is there a relationship or not? That's a hypothesis test. There must be a p-value somewhere that can help me answer that question. That's just my first pass at making sense of statistics in terms of the types of questions you're asking. How are people feeling so far about that categorization? Cool. All right. So just some history. In the 1890s to 1920s, most of these things were invented in around that time. Scatter plots. I mean, the graphs are a whole other thing. Like the bar graph was invented in like 715 something by Playfair to show the thrilling data of yeast exports from England. And lots of graphs were invented later. The box plot, did you do box plots? The box plot wasn't invented until 1977. It's really late. But most of the others were invented like early 1900s. And your chi-squared tests and your t-tests and regression, that was all invented by basically Pearson and Fisher between 1890 and 1920. And we've got some other fiddly bits and pieces that we've added along the way to make them a little bit better, but really they haven't gotten much better since then. And the modern statistics is all done with machine learning, and which is really just regression, but we like to call it machine learning because it sounds fancy. Modern statistics happened after the advent of the computer, and we can do a lot more cool stuff that doesn't require a lot of this theory. It's more numerical methods-y, unfortunately. And linear algebra, yay. So that's the history. And one of the reasons why there are F statistics and stuff like that when you do things is because it's named after Fisher, who invented a lot of this stuff and was very, very clever, but refused to explain anything that he thought was obvious. And the tradition has continued in maths teaching to this day. Yeah, it's very sad. He was not a very nice person. Believed in breeding out undesirable races. Anyway, so yes. Okay, so sorry, got myself distracted. Moving on. Okay, so there are lots of different situations you can be in and different kinds of data you can have. And the different kinds of data dictates the best way to analyze that data. And there are two main kinds of data. There is categorical. And there is, I call it numerical. Your lecturer probably calls it quantitative. I don't know. Did they talk about this? Categorical versus quantitative? But I don't know. I call it numerical, but sometimes it's called quantitative. Quantitative, yes. It doesn't really matter. The idea is that's the types of data you have. And before you even get to the data, damn it, I should have done this beforehand. Before you even get to the data, you need to decide what object it is that you are recording information about. In statistics theory, they call that the subject of the experiment. So the thing you record data on, and you need to think very carefully about what the thing is. Is it, it could be, an individual bolt. It could be the machine that makes the bolts. It could be the entire factory. You need to know what your data belongs to. So so just last week, a student came to me from veterinary science, and she was interested in when people make a complaint to the council about a cat, whether the way that they made that complaint makes a difference to whether the cat gets euthanized or not eventually. Serious stuff. And so you'd think that the cat itself is the subject. You can say or the complaint, what kind of complaint it was and what's the outcome for the cat. That's great, but actually she didn't have information about how many cats were euthanized and how many complaints there were, but didn't know which one went with which one. And she had that data once per month. So her subjects were actually months, not individual cats. And it's the same thing here. I could measure, the diameter of the particular bolt, but if all I had was the average diameter of the bolts for a particular day, then the day would be my subject. You need to know who it belongs to. Can you say that this belongs to one individual thing, or does it belong to the group? It's really important. Yeah, and that's really important for probability as much as it is for stats. So when you're doing the binomial probability, the number of how many of your objects were overweight or whatever, that doesn't belong to any one object, it belongs to the whole group. So you need to think about the group as your subject. That makes a difference to how the probability works out. Okay, so you need to choose how the subjects are, and when you think about the individual subjects and what's written down about that individual thing, you can either write down words or numbers. You can tell that something that looks like a number is not really a number if when you subtract them, it doesn't mean anything. Like if talking about how far apart they are is meaningless, then it's really a word. So for example, you could have tutorial group 1 and tutorial group 2. Tutorial group 2 isn't one more than tutorial group 1, they're just different. And so that number that says which group tutorial you're in isn't really a number, it's just a word. It could just as easily have been red and blue. That's just important to think about. But other than that, the numbers are pretty obvious as numbers. It's just that some numbers are really words. And usually if they're just talking about groups that you're in, then they're words. This is important. And when I think of these in my head, categorical variables are putting things in categories, which are boxes that you can put things in. So, oh, these ones are underweight, these ones are overweight. Or if you like, they could be numbers, and numbers are measured on a scale. And when you draw them on a graph, they're drawn on a scale. Okay. So almost all statistics things are about the relationships between variables in your data. These are called variables, by the way. Between variables in your data. They're really about variables in the world. They're really about concepts in the world, but the only way that you can analyze them is to turn them into variables in your data. And so if you're interested in, you know, grumpiness of people complaining about cats and life or death of the cat, then you can record that as, you know, cat is a nuisance versus cat is just stray, and that's a category, 2 categories, and then just life or death, and that's categories as well. But you could also just have, you know, a rating out of 10 for how grumpy the person calling the council is as well, and that would be a number. Okay, so for example, you could also measure the actual diameter of your bolts, but you could also just record whether they are over or under, and that would be a category. So you get to decide that sort of thing. Okay, cool. Right, so some questions are literally about a single variable all by themselves, such as, what is the mean weight of cereal in the cereal packets? Think of the objects, the cereal packets themselves, and each of them has a weight of cereal. That's my data. That's a numerical variable. And I have one question about that data, which is, what's the mean? And that's a what's this number question. So I would calculate a confidence interval. But the question of, is it more than what the packet says it is? That would be a yes or no question, which would be a hypothesis test. But if I was saying, does which person is operating the quality control system in the factory make a difference to the weight of the cereal, then the answer would, that's a yes or no question, but it's now about the relationship between a category, which is which person it is, and a number, which is how much it weighs. Just stuff to think about. Okay, so here we go. Right, so I'm going to run through the list of things in your table here. My understanding of the way the past, in the past, sorry, just a second, I'm looking for that table. In the past, there's been a table in the lecture notes here, and past lecturers have put this table on the formula sheet. So if your lecturer this semester is anything like past semester ones, they will include just this table on the stats formula sheet, and possibly a couple of formulas for probability. Just that's what to expect. We'll know soon enough. Okay. So, first question. This box is the variable. So if you have a variable that is a number, sorry, and you want to know what's the mean, or this would be a confidence interval, or is the mean equal to this particular number, that would be a hypothesis test. And you have your individuals each have a number that goes with them. Then there are 2 situations, depending on whether you know what the standard deviation is or is not, which just I find you'd never know, right? It's as if you're going to know what the standard deviation for the whole population really is. Anyway. Then that's what a t-test is for. A one sample t-test is designed for that situation. I have individual numbers recorded on my individual things, and I want to know what's the mean. And the t-test is for that. I've heard it called the one sample t-test. There is also a one sample z-test that goes with this as well. So the t-test goes with the situation of, actually, I do know the standard deviation. And that would be a, damn it, don't know the standard deviation. That's the one sample t-test. Do know the standard deviation. That's the one sample z-test. I would not expect your lecturer to do this at all in the exam. If you got Jono, I would not expect him to put this in the exam, because he believes that this is just a stepping stone to learning about this. But you never know. There are rules about what people think should be in a stats course, and Jono doesn't always get to decide those rules. Okay. I'm just going to interpret this table. So I think about this differently, but this says parameter is mu, which is usually the mean. And so parameter is a number that I'm wondering about, a number that belongs to the distribution, therefore a number that I don't actually know. So when I'm asked, when it has a parameter, it's a number I don't know. And so my question is usually about the number I don't know. This number is about a mean. What's the mean? What's the mean? That's my parameter. And we're asking, yep. So this table gives me a lot of information. I'm just going to draw the line in the table. So this is the line of the table that goes with this. It says normal mean, sigma not known, sigma squared not known, parameter, estimate, parameter is mu, estimate is x bar, standard error is s en route n, reference distribution t n minus 1. This is supposedly enough information for you to figure out how to do this hypothesis test. I mean, other than, you know, I've got the data and I'm going to ask MATLAB to do it for me. Yep. S is the standard deviation. If it was the variance, it would be s squared. We only have a name for what s squared is because of Fisher. Because he discovered that the mathematics was easier when you were working with the s squareds than with the s, because that gets rid of the annoying square root in the formula. So, yeah. So this is apparently enough information to figure this out. And the reason it's enough information to figure this out is that you can build both the confidence interval and the hypothesis test from this information. So the way the general theory of statistics works here is that if I take individuals, I'm going to make them people, but they're not usually in engineering. They each have a number, and you've got a collection of them. And from that, you can calculate the sample mean and the sample standard deviation. And there's n individuals. These things are what goes into this formula here. And what I would like to do in hypothesis testing is the idea of it is the idea of it is that the world is full of probability, and anything that I could calculate somewhere in the philosophical background of the universe, there's a great big keeper of the distributions that says, oh, you've got a number. What are the options for what that number could be, and how likely are they all? Roll some dice, and ta-da, this is the answer you get today. And anytime any number that could be different, that varies, happens, you get a different answer based on this distribution. And that's what a distribution is. It's a description of how likely everything is and how all the options and how likely they are. Now, for each individual person here, there's a chance they all have their own numbers, and pick a random person. There's a chance of them getting a particular number and every number has its probability. But I'm interested in all of the groups of n people that I could possibly have had. When I'm doing statistics, I'm wondering about all the things that could have happened, not just the thing that did happen. I've got a group of, say, 10 people. I've recorded a number on them, and I want to know what could have happened. And that's too complicated. So I just calculate the mean and then go, what could have happened for the mean from 10 people? What means could have happened that I could have had? And I think, well, if the mean for all individuals really is this number mu, then these are the things that could have happened for a group of 10 people. This is my group of 10 people. How do they compare to all the things that could have happened? That's the thing. And I find the could have is useful for me. And so we calculate this thing. X bar minus the mu I'm thinking of. The particular value of mu I'm wondering about whether it really is equal to, and divided by this thing. So this is the estimate minus the one I expect it to be divided by the standard error. And this calculation, Gossett, who worked for Guinness, discovered that if you did this calculation, if you assumed that this data came from a normal distribution, then you could know what the keeper of the distributions, what distribution they were using to find this thing. So if you said, this is my entire process, I'm going to collect 10 individuals, I'm going to record their numbers, going to calculate the mean, we're going to subtract the mu and divide by the S on root n, and that'll give me a number. And I imagine all the numbers that this thing could possibly have produced, then those things together come from a t distribution with n minus 1 degrees of freedom. Yay, yep. That is the t-test. And so that's why we call this t. When the t-test was first invented, it was called Z, and then someone else said, but we've already used Z, so we have to choose a different letter. Yeah. Yeah, they actually said, oh, Z, that's great, because it was always Z before. So if you know that this sigma, if it's a sigma, not an S, then it's a Z and not a T. And they were just using Z as a general word for test statistic. And then someone said, oh, but we already expect Z to be normal. We should use a different letter. Yep. Traditionally, we're not up to that yet, but I'll get asked that in just a second. So this is great. What we have is that our data produces this number, and this produces this number, and these are all the options that the number could have been if it really is true that the null, I call it a null hypothesis. If the mu really is this number I'm thinking of, which I'm going to call mu naught, because I'll never know what mu really is, because it's unknown, it's a parameter, you'll never know the parameter. If it really is this thing I'm thinking, if it really is 500 grams for my cereal, or if it really is like a millimeter for my, well, it's probably on like 0.01 really for expansion of like a metal object, or if it really is whatever it really is, or 0, then I put that here and I compare, and it should come out to a t distribution. But I want to compare my value of t to all the values of t that could have happened. And according to Gossett, it's this shape, and this is my value of t, and these are all the t's that could have happened, and this is how likely they all are, and these are the ones that are further away from expected than mine, and that area is the p-value. And if that p-value is under 0.05, it is tradition to declare this as significant and conclude that no, actually, the mu is not the mu naught I was thinking of. Because if something's unlikely, then I don't believe the situation I'm in. Well, I thought I might be in. So I think, a useful way of saying it, but never tell a statistician this, that a p-value is a measure of how much you believe the null hypothesis. The lower it is, the less you believe the null hypothesis. Yeah. Okay. That's a t-test, the one sample t-test. it's not actually very interesting because most of the time your research questions, if you're really doing research, are not about one number. They're about the relationships between things. Well, I'm actually going to draw it the other way. So what if I am still interested in a number, like the weight of my cereal? I have cereal on the mind because I've just been learning about the dwarf planet Ceres, who's named after the god of cereal. Yep.
Wait for that. So if it's less than 0.05, keep it.
So yeah, it's tradition. So the question we're asking is the mean equal to mu naught? That's the question we're asking.
Yeah.
And the null hypothesis is that it is equal to mu naught.
Yeah.
Cool. Because you have to pick a number, otherwise you can't do your calculations. Yeah. So that's why that's the null hypothesis. And then the answer, so under the assumption that this is the truth, the probability of getting your data, I'm going to have a few options. If this was like 0.02, then you would normally declare that it's the answer to this question is no. No, mu is not mu naught. But you don't normally say it that way. You would say there is strong evidence to suggest that the mean is not.
Because it's you have too much area under the bell curve.
Yeah, not enough area, not enough area worse than mine. Like say, the point you're trying to make is that your t that you calculated is really far out in the edges.
Yeah.
So the further out it is, the lower p-value it is, and the further out it is, the less ordinary it is.
The less likely it is to happen.
Yeah.
Yeah.
So reject the null hypothesis and conclude that there is strong evidence to suggest that it is not true. Evidence suggests the mean is not that. And you normally have to do it as a sentence because that's tradition. But if my p-value came out to say, 0.13, then you'd say, does your work lecturer use retain? And say that there's no evidence to suggest the mean is not whatever mu naught is. And that is double negative, right? No evidence suggests that it's not, but that is what you've done. You've been looking for evidence to suggest it's not. And that's the problem with hypothesis tests. They're double negatives, but that's the way we play. Yeah. Is this answering your questions about how you're allowed to say things? Okay, good. So when I teach the med students this statistics, they don't have to do any of the calculations. They just have to interpret published research articles to see if they seem reasonable. And I don't talk about null hypotheses and crap like that. I just say, what's the research question and what's the answer that it says they are? You guys have to talk about null hypotheses and stuff. I'm sorry. It's important, but yeah, whatever. It's important for you today. But what the message you want to take beyond your exam is that it's trying to answer a yes or no question, and you pick the answer to the yes or no question that goes with being a single number, and that's the null hypothesis. And that's great. So there is another single number question that you actually ask in statistics. So I'm not going to do them in the order they're presented. What if your data was still just a single piece of data from each individual, but the piece of data you're recording isn't a number, but a category? A, B, C, it could just be A and B, it could be yes and no, doesn't really matter. It could be categories of any kind. Oh, sorry, missed a question. Table is not included on formula sheet. If someone finds the formula sheet in their All right, well, we'll know soon, but if it's not, then that's sad and you'll have to just remember some of this stuff. But if I know Jono the way I know Jono, he will include all the information you need. If I know Chanel the way I know Chanel, he'll include it. He listens to Jono. Okay. All the people who teach stats up in the School of Maths know each other very well and actually talk about their courses with each other. And so it's likely that it'll be okay. If not, I'm very sorry. And you can come and cry to me in the Maths Learning Centre and we'll figure out what to do afterwards, okay? We're open all week. Okay. What if you've got a question about just a category? Every individual has a category reported about it. There might be several categories. There might be only two. So what if your question is, what proportion in category A, or in category B, or in category C, just in one of the categories? That's a what's this number question. A proportion is a number. And so that would be answered with a confidence interval. But if your question is the proportion in category A equal to 50%, then that is a hypothesis test situation. And that hypothesis test is concerning a proportion. And you have hypothesis test for proportions. It's called the binomial test. And the reason it's called binomial is because there's two answers for every individual. They are in category A or they are not. So we've lumped B and C into just not A. Okay, and that binomial test, according to the table, is parameter P. So in my story, the P is that 50%, which is 0.5, because statisticians don't like percentages unless they're talking about p-values. Don't get me confidence levels. Parameter P, the estimate is called P hat, which is whatever it is in the sample. And the standard error is and here we go. I've got all my individuals. Some of them are in A and some of them are in not A. Right, and I count the number of A's. And actually what I want is the proportion of A's, which is what the P hat is. And then I calculate Z, which is P hat minus the parameter from the normal null hypothesis divided by the standard error. And this comes from a normal distribution with mean 0 and standard deviation 1, which is what Z stands for, which is the infinity of T distribution, by the way. So you know how there's like Tn minus 1? Like there's a T distribution with 5 degrees of freedom, there's a T distribution with 17 degrees of freedom, there's a T distribution with 500 degrees of freedom, and the T distribution with infinity degrees of freedom is Z, just so you know. I imagine the T distributions as living in a big apartment tower, and you just like press the button on the lift and it takes you to the correct floor. And so when the Lego movie came out and Lord Business lived on the infinitieth floor, this one is the Z distribution. So that's how my brain works. Okay, so that's how you calculate it. And so when you get that number, you have to ask the Z distribution what the p-value is, instead of the T distribution what the p-value is. But the same rule applies if your p-value is under whatever the limit is, 0.05, they might tell you a different one, but it's usually 0.05. Then you declare that actually no, the proportion is not 50% or whatever it was that you were looking at. So in essence, and this is the important thing to do with these courses, it is the same kind of question as the T test for a mean. This is the Z test for proportion, but because it came from the individuals had words about them, and so the way that we created our statistic was a completely different way that we created this statistic because the data is different. each individual just has a word and I just add up how many of them there are. Whereas this one, each individual has a number and I average them. And so have to do a different kind of calculation. But the calculation I do is similar. It's still thing minus null hypothesis thing divided by other thing. And that's why they give you that table so that you can know which bit goes in which spot of the calculation. Yeah. I actually just say if it's a hypothesis test, damn it, this is P naught for the hypothesis test. Sorry about that. If you want to do a confidence interval, so you've decided that actually no, the proportion is not 50%, and then you're asking what actually is the proportion. That's what a confidence interval is for. And I would say that the proportion is, well, we're 95% confident that the proportion is in this interval. And one end will be P hat plus or minus Z star. Do they do Z star? Is that how they do this? Yeah. Times the standard error. And so one end is with the minus and the other end is with the plus. And this is all in the notes. I'm just trying to organize it. And that's how confidence intervals work. So the question of, is the mean 50%? That's this one. The question of what actually is the mean, what options, not mean, what actually is the proportion, what could it be? That's this. So when you're doing t-test, the formula is the same. You use this bit is the same, like this s on root n is the same either way. But when you're doing proportions, it's P naught here and it's P hat here. Because you can't use P naught because you've already concluded that the correct answer for P is not P naught when you've done the confidence interval. To be honest, it probably doesn't matter that much, but it does matter to the person who's giving you marks in your exam. So, which is the worst kind of mattering. But anyway. Thoughts or questions about this? Right. So we have one more kind of question that we can ask about a single variable that's category. This question of what proportion is in this category, or is the proportion in this category a specific number? That's what we've done. But what if I wanted to ask about all the categories simultaneously? What if I wanted to say, are all the categories arranged this way? No, that is a very important, excellent question. So this Z, so the thing is that this one, we know what this is in this one, but we have to calculate this from our data. In this one, we know what this is. And we have to calculate, because technically this is what the answer for P could be. So in this one, we go, well, this is where the P would go, and we're going to choose P naught to go in that spot. This one, we're going to do it. And this is the Z that would have given us exactly 0.05 if I had gotten a p-value back here. So this one, this Z, I get a p-value from it, and you get like your little normal distribution, and there's an area there. And that's the Z that came out. If that Z was, you get a certain point and you get a p-value from it, and if that p-value is below 0.05, then you would reject. If it's above 0.05, then you retain. If it was exactly 0.05, you wouldn't actually know what to do. And you'd probably just, it wouldn't be exactly 0.05 because you'd round it off anyway, and so you'd just pick which side it's on. And if you were really reporting research, you're saying it's exactly 0.05, we should probably do more research on this. But if it was exactly 0.05, then you'd be right on the edge of rejecting and retaining. And that's what this Z star is. The Z that would be right on the edge of rejecting and retaining. We're exactly at that 0.05 level, the Z that would give you that. You would have to ask a machine which one it was. And it'd be like, Z, I don't know what it is in MATLAB, but in Excel, it's like z.inv. Yeah, or there'd be a table that give you some information about it. For a Z distribution, if it's 1.95, if it's 0.05, it's exactly 1.96 is the correct answer. But over here, if I was doing this confidence interval, I'd use a T star, and then be a different T star for every degrees of freedom. And they would all be a little bit more than 1.96, getting closer and closer to 1.96 as we go up the floors to the infinitieth floor. But you would need to ask your machine how to do that, which would be in the MATLAB code somewhere for the T distribution. Sorry, norm inverse, that'll be it. Yeah, so let's talk about that just a second. So the way that MATLAB works, in most statistics programs is it will only tell you, so the norm, is it called norm inv? Yeah, norm inv. Is there a dot? It's just norm inv? Norm inv and then brackets and the argument. Yeah. And if you don't put any, and there's optional arguments, right? If you just don't put anything in and just put that, it'll just assume it's the Z distribution, or do you have to put the 0 and the 1 in? Okay. Something like that? I've got a 0.05. Okay, yeah. Cool, okay. So the idea is that if you've got a Z here, the way that MATLAB works is it only tells you what's on the left-hand side of your Z. It doesn't tell you what's on the right-hand side, and doesn't tell you what's on both sides simultaneously. The picture you've got is this picture, and you need both of them together to be 0.05, which means you need this bit over here to just be 0.025. So together they're 0.05. And so this position here that happens to have 0.025 in it will be norm inv of 0.025. If I just had a random Z, so this is my Z star, if I had a random Z in a particular spot and I wanted to know what this area is, so if I know what this is, say suppose this came out as like 2.3, for example, and I wanted to know what this p-value was, I would need to ask MATLAB what these areas are, and MATLAB can't tell me areas above, it can only tell me areas below. So I would look at this, and I would choose the negative version. It would be norm dist, is it? CDF, yay! And I would put in minus 2.3 and the 0 and the 1, and it would tell me what this bit is. And so the p-value, because there's two of them, would be 2 times that answer. Or you could use a statistics program that just does all of that for you, but they want you to be able to do the calculations as well because they believe it's important, which it is. But there are grades of importance. So how do you feel about using the MATLAB to do that stuff? Right, so in the exam, my instinct is they're probably going to give you several MATLAB codes and what their answer is, and you're going to have to pick the right one. That's my guess. Okay. They do try and match what they do in the tutorials. Yeah. Okay. So what if your question was actually, you've got a thing with several things and you say, is this the correct list of proportions? So you've got a proportion for every category and you're asking, is this the correct list? You know, e.g., is it 20%, 50%, and 30%? Though if it's a statistician, they would say 0.2 and 0.5 and 0.3 because they don't like percentages. But that's the question. Is that the correct list? Which is a yes or no question, but it's asking about several proportions simultaneously instead of just one proportion. So there is a test for that. It's called the ChiSquared Test for goodness of fit. Whoa. And the reason it's called a chi-squared test is because instead of using a z distribution or a t distribution, you use the chi-squared distribution. And chi is the Greek letter chi. The capital is an x. This is the lowercase chi. I believe in Greek it's ch, but we don't have that sound in English, so it's just k. It's the same letter at the beginning of Christmas, at the beginning of Christ. There you go, in Greek. Not that any of that's important, but sometimes it just, talk about it a bit. It's like remembering someone's name. You just got to talk about it a bit and then you might have a chance. Okay, so it's the chi-squared test. That's chi-squared. Okay, and just so you know how I wrote that, so it's a diagonal down backslash, forward slash, and then this one's curved, as opposed to both of them being curved, which is what it is in a script X in algebra. So yeah. Okay, chi-squared test for goodness of fit. Now, it uses the chi-squared distribution, and it was invented by Pearson because he loved the chi-squared distribution. And it goes like this. You have to take your individuals, which all have a category, like, you know, this one says A, this one says B, this one says A as well, and so on. They all have a category of their own. And then you create a table of how many of each there is. And this is the table of observed frequencies. And there's like a total at the end. And then you compare that to what you would have expected to see if, in fact, the proportions were what you thought they would be. So if it really is 20%, 50%, 30%, so I'm just going to do as an example, I'm going to stick some numbers in. Maybe there's... what do we got? 40, 50, 60, something like that. So if it really was 20%, 50%, 30%, then out of 75, I would have expected 20% of the 75 to be in this spot, and 50% of the 75 to be in this spot, and 30% of the 75 to be in this spot. So this should be 0.2 times 75 and 0.5 times 75 and 0.3 times 75. That's what I would have expected to be in those spots if it really was set out this way. I mean, it's never going to be exactly that if you just take random people from the group. Sometimes you're going to get a few more that are in category A and a few less are in category B. It'll work out that way, but this is what you would have expected on average. And so what I need to do is compare each of those to the one that it would have been. Oh, 15, cool. So this one is coming out exactly as I expected it to. This one's come out to be more than I would have expected, and this one's come out to be slightly less than I would have expected. And so what I need to do is need to compare those to each other. And there are lots of things I could do, but I need to calculate a single number that I know the distribution of. Because the whole purpose of this is to say, hey, this number, what are all the things this number could have been? And so the calculation I do is this. I'm actually literally calling it x squared because it's not the chi-squared distribution. I need to do observed minus expected squared divided by expected. And then observed minus expected squared divided by expected. And the same for this last one. I don't have room for that. For me, I find it easier to do it like all in a table. I need to calculate these three things separately. Pretty sure it's observed minus expected squared over expected. Yes. Okay. And then I add them all up and I get this answer, whatever it is. And then I think, okay, if the proportions really were arranged that way, what are all the options for what this answer could have been? And those options come from a chi-squared distribution with a certain number of degrees of freedom. And the degrees of freedom is one less than the number of boxes I was using in my categories. I had 3 boxes here. I will use 2 here. If it had, you know, A, B, C, D, E total, then it would have been coming from a chi-squared distribution with 4 degrees of freedom because it's all but 1 box. And same deal, look it up in your table, except very important thing to note, chi-squared distribution is this shape and it stops at 0. And so it's only one side that you do. You don't do both sides. You don't add it up. You only do one side. So if I got this number here, I would go chi PDF. I don't know what it is. It's probably chi CDF, and then you'd put in your number, and you'd put in the degrees of freedom, and then you'd have to go 1 minus that because this always gives you the left-hand side, and you want the right-hand side. Something like that. Cool. So I would like someone to articulate what the difference is, well, what is similar and what is different between the Z test for a single proportion and the chi-squared test for goodness of fit. Can't find it now. Sorry? CDF. It was PDF and then I was wrong and then I didn't do a good job of turning it into the right thing. So what's similar about those two? The last 2 tests I just did. Important questions to ask yourself. This is why I'm getting you to do it. Or different. Can I just say, when I next answer this, I'm going to tell you some answers now and it can be really mundane. For example, one of them uses Z and the other one uses chi-squared. One of them uses is only referencing one category, whereas the other one references all the categories simultaneously. They're both about one category recorded about individuals. It's not about relationships between things. It's just about one variable. They're both about one variable. It's just that one of them, the variable only has a yes or no, and the other one, the variable has multiple different categories. So one thing I will say to you, there's nothing stopping you doing the chi-squared test when there's only 2 categories. Chi-squared test for goodness of fit. And in which case it will give you the same p-value as the Z test for one proportion. Because asking is, if there's 2 of them, asking is this one 20% is the same as asking are both of them 20%, 80% together. And they'll actually give you the same answer, the 2, yeah. So if you had done the chi-squared test for goodness of fit on 2 of them, and separately asked, is this one 20%, like saying, is it 2080? Or if you've done the Z test with is this one 20%? Or a Z test being, is this one 80%? They would have all given you the same p-value, which is really cool. And in fact, the chi-squared statistic would have been the square of the Z statistic you got in the other one. Just fabulous. Yeah. So there's nothing stopping you using a chi-squared test when there's only 2 categories. It's just that You can't get a confidence interval out of this one. So you know how the other one had the standard error and the p hat and the whatever, and you could arrange that either as a fraction and that would give you the test statistic, or you arrange it as a z star and that would give you the confidence interval. This one can't be rearranged into a confidence interval, which is why it's in a separate category in your notes, because it doesn't have the confidence interval version to go with it. But in terms of what it's designed to do, it's asking a really similar question. All right. Okay, all the other tests that you have are about the relationship between two ideas. Those three that I've mentioned so far are only about one idea at a time. Who's in what category for the proportions and the chi-squared, or what number does everybody have? But most of them are about relationships. So what if you are still interested in a number, but you want to know, does it matter which category you're in? Does it make a difference to the number that happens? So for example, 2 locations. Is the average soil pH the same? Is a perfectly good question that goes with this situation. Whereas these are the location and this is the pH, for example. Or it could be before I got my, I've got 2 different machines that make a part for my robot, and I want to know if what the diameter is it different across the 2 machines? The machine doesn't make a difference to this. So the idea, and it could be 2 situations, it could be 2 different locations. Do they make a difference to the number result, basically? You know, there's lots of ways that you can pitch it, and there's many things that happen. But the idea is that that's the idea. There's 2 different situations, and does it make a difference to the number result? And what that means is that you're going to have subjects which have numbers recorded about them, and possibly, and also what situation you recorded that number in is going to be recorded too. And the situation you're in is a category, and the number is a number. And this is what the paired and the unpaired t-tests are designed for. The independent samples and the paired t-tests are designed for this question. But the difference between them is whether every individual is in both of these situations or whether they're all only in one situation. My individuals are people, I'm sorry, because it's the easiest thing to draw. Everybody's either in both situations, and you record this number in both situations for every individual. And your data would tend to look like this. Person 1, 2, 3, 4, 5. And then you've got the number in situation A, and there's like a number for each person. And you've got situation B, and there's a number for each person. That's what the data tends to look like in this story. And this situation is what the paired t-test is designed for. Ah, crap. The pair that they're referring to in the name there is the pair of data that each person has. Every person has a pair of numbers, or petri dish, or factory, or day, or it doesn't have to be people. Pair of numbers. Yeah. And that's why it's called a paired t-test, because the numbers are paired up because they belong to the same individual. But it could be set up this way. And every individual has a different category. Different individuals are in different situations. And this would tend to look like this. So this is in situation, these people are in situation A and these people are in situation B. and they all have a number outcome. So the data will look quite different. There'll be a whole column of categories and there'll be a column of numbers, whereas the other one tends to have 2 columns of numbers. I prefer to draw the picture like this because it helps me focus. But if each individual is only measured in one situation, it's not going to be a paired t-test, because in a paired t-test, everybody's in both situations. So this is the 2 sample, the independent, oh, damn it. 2 sample t-test. And they work really differently because the kind of data you have is different. So in this one, we actually calculate the separate means from the 2 groups, x1 bar and x2 bar, and we use those in our calculation. In this one, we calculate the difference first. No room, David. The difference first, and then calculate the mean, d bar. And that's how they're different from each other. They're similar because they're both trying to answer the same question. They're both answering the question as, does being in this category make a difference to the outcome of this number? And the way that your lecturer would pitch this, if being in this category doesn't make a difference to this number, then on average, this difference should be 0. If it doesn't make a difference, the difference should be 0 on average. And so your calculation for a t-test would be damn it, there should probably be a capital D bar. There should be a mu D, sorry. The mean of the differences. Sorry about that. What does your lecturer call it? Delta. Haha, fabulous. Okay. Delta, that's what your lecturer calls it, which is the true mean difference. That makes sense. Greek letter delta, delta for D, fabulous. What's that? Yeah, the delta goes with D bar in the same way that mu goes with X bar, because it doesn't really match linguistically, but there you go. Yeah, but this is the calculation. You don't technically have to include the 0, but that's the number you're comparing it to. And this is the standard deviation of the differences here. And this will come from a t-distribution with n-1 degrees of freedom, where n is the number of people involved. And it's exactly the same as the 1 sample t-test. In fact, if someone said, I've recorded them before and after, and this is the differences, and all they gave you is this data, then you'd be doing a 1 sample t-test. That's pretty much the deal. But when you talk about the null hypothesis, you'd say, you know, let be the true mean difference, then null hypothesis is that delta is 0. Now, you're probably not going to be able to write that sort of stuff in your exam, but that's the idea. You're supposed to tell them what the delta stands for. But the other one, the 2 sample t-test, you calculate the X bar and the mean separately for the 2 separate groups. I mean, I would call it X bar A and X bar B, but you know, it's traditional to call them 1 and 2. And so in the notes, it says that you'll go mu1 is the true mean in situation A, and mu2 is the true mean in situation B. Then the null hypothesis is that mu1 is equal to mu2, which is the same as mu1 minus mu2 being 0. The reason I've done that is because now I have a number I can compare to. And so in their notes, they talk about mu1 minus mu2. And so I'm going to go, okay, x1 bar minus x2 bar minus 0, which is what I'm comparing it to, divided by the standard error, which in the table says S1 squared over N1 plus S2 squared over N2. And that is a t-statistic. And that t-statistic has 8 degrees of freedom, which if you got the computer to do it for you, it would calculate the degrees of freedom all by itself. And it would be some like wicked decimal. But for the purposes of doing it by hand, you usually take the smaller of the n minus 1s from the two groups. Yeah. Where n is smallest of n1 and n2. But it's actually a bit bigger than that, the correct one to choose. But that was one of the things that came in after, you know, a couple, maybe 50 years after the t-test was first invented, like that whole thing. The important thing is being able to decide between which one you've got. And it's all about how the data is arranged. So you need to look very closely and notice whether the thing has happened, whether the measurement of the number has happened more than once for every individual. If it's happened twice for every individual, it must be a paired situation. Yeah. How are we feeling? All right. And just like we can see whether a category makes a difference to a number, we can see whether a category makes a difference to a category as well. The one I use with the med students is, does having chili in your meal make a difference to your body, make a difference to whether you feel hot or not? I'm not going to measure people's temperature. I'm just going to ask them, do you feel hot? Yes or no? Right. And so you pick one of those outcomes to be yes, and you say, does it make a difference to how likely that is to happen? So it's usually this situation. And you're going to ask yourself is, does the category make a difference? So situation make a difference to the outcome category. That's the question you're asking. And there are two ways to deal with it. One is to try and use all the categories simultaneously, and that's what the ChiSquared test does. And the other is to focus on one category and say, does it change how likely that one category is? So you could ask, you've got two options. One option is, does the situation make a difference to the proportion in category A or category B or whatever category it is? And then you're saying that P1 is the proportion in category A in situation 1, and P2 is a proportion in category A in situation B in situation 2, and the null hypothesis is that the two proportions are equal to each other. So this category is usually doesn't look like it's two categories. It's usually just a yes. You know, does the way that I treat my fabric make a difference to whether it becomes moldy? And the category you're looking for is becoming moldy. Right? You could just as easily do the one of not becoming moldy, but it doesn't make as much sense. And then that's here. So then you're saying that you do the P1 hat and the P2 hat. They've got their own proportions, and then you do a calculation. So it will be a Z statistic this time because that's how proportions work. Technically minus 0, because if they were equal, then it would be 0, that difference. And then you do this fabulous thing with the P1 hat 1 minus P1 hat over N1 plus P2 hat 1 minus P2 hat over N2. And that should come from a normal distribution with mean 0 and 1. And that's where I'm going to look up my p-value in. But the process of deciding what the p-value tells you is the same. You might get a p-value of 0.03, and you'd say there is evidence, strong evidence to suggest that the proportions are not equal, and therefore it does make a difference which category you're in. The situation does make a difference to whether you're moldy, something like that. But there's a different way of dealing with this, which is to look at all the categories simultaneously. Instead of just focusing on one and saying, hey, does it have, does that proportion change? Because this I can use to create a confidence interval if I want, but if I don't want a confidence interval, and if I didn't care how many categories were involved on either side, then I could use all the categories simultaneously and still ask the same question. Does the situation make a difference to the outcome category? Which is the same as saying, is there an association between these two variables? Which is why it's called the ChiSquared test for independence. You say, are these variables independent? It's the same question. If one of them doesn't make a difference to the other one, then they're independent. And that's what the ChiSquared test for independence says. And it'll work in the 2x2 situation we had before, where there were 2 situations and 2 outcomes. That'll work. It'll work with 5 situations and 3 outcomes. But the more categories you have, the more data you need to be able to get a good p-value. And the way it works is you'll have a table where one direction is what this one is, and the other direction is what this one is. So you go like the situation 1, 2, 3, 4, 5, and the outcome A, B, C, and you have a great big table like this, and you have numbers in all these spots. And you also have totals. And we're going to do the same thing we did with the other chi-squared test. We're going to, oh crap, I'm going to have to deal with that. Don't like it being up here because it's too high. But anyway. Yes, so these categories, there will be numbers in these categories from your actual data. And you'll go through people in or objects in situation 1, and you'll say how many in each category, outcome category there are, ones in situation 2, how many in each outcome category, and so on. And then you'll need to figure out, this is the observed one, what would have happened if I did think that this situation didn't make a difference with this category. So if this didn't make a difference to this, I'd expect the same percentages in A, B, C in every group. That's the idea. So I figure out what percentage actually end up in A, B, and C using the totals, and those percentages of each group end up in these spots. So I'll do it smaller than that. So what if it was like this? No, I don't want a 5. So if it was like this, then I've got the total number of A's is 30, 40, 50, 65. And the total number of B's is 40, 50, 75. I really should have been more careful about this. And these, there's 40 of those, and there's 30 of those, and there's 70 of those. And there's in total 140 of them. Okay. So if which 1, 2, 3 you're in didn't make a difference to which AB you ended up in, then they should all be 65 out of 140, that percentage. Come on, you can do it. That's like 46%. So 46% of them ended up in category A and 54% of them ended up in category B. If which situation didn't make a difference, it should still be 46% in A and 54% in B here and here and here. They should all be the same. I mean, they're never going to be quite the same because it's random stuff and you're just randomly choosing people, but it should be approximately the same. And that's what we're going to figure out. So we're going to go expected I would expect it here for 46% of those 40 people to end up in this spot. Because 46% of them are A's, so I should expect 40% of these people to be A's as well. And so that is the 65 out of the 140 times the 40, and that's what goes in this spot here. And I'm going to just do that calculation out here. So 65 out of 140 are A's total, and that proportion of the A of the people in situation 1 should be A. And you do that for every box. How are we feeling about this? Should be 18.6. It's okay. The shortcut is it's the row column row total times the column total divided by the grand total. It'll always work out to the right answer, but I can never remember that formula, but I can remember this percentage thing. So you do all of those, and once you've figured out what all those numbers are, then you do observed minus expected squared divided by expected. And you do that for every box and you add them all up. And that is your chi-squared statistic. And it comes from a chi-squared statistic with a number of degrees of freedom, which is, see this table here I just made, which has all the categories in it, just ignoring the totals. I'm going to remove one row and one column, and the number of boxes left, that's the degrees of freedom. Because if I keep the totals the same and I change these two numbers, then all the other numbers will have to be whatever they are. Like if there's 65 people in this row and there's 10 here and 20 here, then there's guaranteed to be 35 in the last one. So these are the ones I'm capable of changing before I have to change everything else automatically. So back here with this one, the degrees of freedom would be remove one row and one column would have been 8. Because that's how much is left when I remove one row and one column from the options available. So they talk about row minus 1 times column minus 1. Well, that's exactly what that is. Remove one row. Now this row minus 1 is 2. Remove one column. Column minus 1 is 4. And then how much is left? 2 times 4. That's the degrees of freedom. Back with the not about relationships, but the goodness of fit one, you can't remove one row and one column because there's only one row. So you just remove one column and the number of boxes left is the degrees of freedom. So that's what it is. And the bigger your table is, the more degrees of freedom it is, which means the harder it is to get a low p-value because the hump in a chi-squared statistic is at the degrees of freedom. And so the hump is further out. Yeah. So that's what they're for. I'm hoping it's helpful to know what they're for. Doing the actual details would require me teaching the whole course again. And the only other hypothesis test that appears in your course, as far as I know, is the one that goes with regression. Does a number make a difference to another number? So does the amount of sleep you have make a difference to your grades? They're two numbers that are related, and that's what regression is for. And I said that regression isn't designed to answer those yes or no questions. And you're right, it's not. It's designed to answer make a prediction sort of question. But the question of are these two numbers related to each other is a yes or no question. And so a p-value should be able to be calculated to answer that question. Are these variables related? That's a yes or no question. And so you should be able to answer it. So if they are related in a linear sort of way, so this is related, this is not related. If they're not related, then it makes no difference what this variable here is. And this will just be random. So if sleep makes no difference to grades, then different people with different amounts of sleeps should on average just have the same grades. That's just how it should work out. And people who are different with different amounts of sleep, with the same amount of sleep, should have just as much difference between them as people with different amounts of sleep. And that's this picture here. This picture here, doesn't matter what X I pick, the Y's are just spread out exactly the same as they are for every one of them. The amount of which X you've got doesn't make any difference to which choices there are for what Y could be. Whereas this one, X's that are further up have further up choices for Y. X's that are further down have further down choices for Y as well. So if what choice for X you have doesn't seem to make any difference to what choice of Y you have, then if you attempt to draw a line of best fit, it should have slope 0. So are these variables related is the same question as, is the slope 0? So if you say that Y is beta naught plus beta 1, do they use this, beta naught and beta 1? Yep. Plus a bit, an epsilon probably, I don't know. If you say this, then the question of are they related is the same as is the slope 0? Because if the slope is 0, then this isn't here and it's just number plus some random crap. And so that would be saying, so the hypothesis of no relationship is the same as the hypothesis of beta 1 is 0. And so you would go looking to find the t statistic that goes with the beta 1, because it is a t test as well. Numerical outcomes. So you would go the t is equal to the beta 1 hat minus 0, because that's what you're comparing it to, divided by the standard error of beta 1 hat, which is what your computer knows how to calculate from its various fancy formulas. And that will be a t statistic. And it will come from a t distribution with n minus 2 degrees of freedom today. So t distributions tend to happen when you calculate things that involve numerical outcomes. Zs tend to happen when you have things with categorical outcomes. And which flavor of t distribution it is in terms of the degrees of freedom depends on how your data is arranged. And what kind of question you're asking. It just so happens that statisticians knew about the t distribution already, and they tried to make these things fit into a t distribution, which is why they do. Yeah. Cool. Any thoughts or questions about the statistics bit? Interpreting slopes, though, you asked about saying the right thing. Like, it's classic in stats to say, you know, interpret the slope coefficient in this regression. And the answer is, there are many ways to say it. Some of them are wrong. And you have to say something, you know, suppose you got in your regression, you know, it would have like intercept and then like sleep. And there'd be coefficients here, there'd be numbers in these spots. It's a table that MATLAB produces. Yeah. I don't know what it puts here, like the coefficient, but I don't know. And there'd be like a standard error, and there'd be a t statistic, and there'd be a p-value, and so on. There'd be a table like that. So let's assume that this came out as like minus 1.8 and 3.2, for example. This is going to be really bad, and it's not going to match with reality, but just pointing it out. Let's suppose that so we've got sleep in minutes and grades in percentage points. Okay. So if I wanted to interpret this slope coefficient here, then I would be saying, sorry? Correct. So on average, I mean, the long version is this, so don't write this down, but the long version that's completely rigorous is that two individuals who are different by 1 minute of sleep on average, like who are different by 1 minute of sleep, you would expect them to be different by 3.2 percentage points. Because it's not like you're actually saying that having an extra amount of sleep will make your grades go up. It's that people who are different by that much are different by this much. Like that's the long version of it. But the way that you say it is that you say an increase of 1, and then go and find the units that the x is measured in, which is minutes of sleep, corresponds to an increase of 3.2 percentage points in grades on average. You must say the words on average somewhere because it is just averages. But there are lots of, grammatically, if it's arranged in a different order, it should be fine. So you could say, you know, people with 1 minute more sleep than others, on average, will have 3.2 percentage point higher grades than others. Than others. Yeah, so that's the most accurate way of saying it. But this is pretty much it. You don't want to say corresponds. Corresponds is fine. You definitely don't want to say causes. Statistics is not capable of telling you about causation at all. That's what experimental design is for. So if you did an actual experiment, then you might have a chance to say causes, but we just don't know. So don't say causes. Don't say leads to. Don't say anything that seems to talk about time order of events either. It's just like corresponds. It's a nice word. Yeah. Again, oh no, see, this is the thing, right? If you were writing a written exam, then there'd be some grace, right? And they'd go, oh, well, this is the only point they lost in the whole thing. That makes a difference between passing and failing, we'll just give it to them. But a computer marked thing is not going to give you that grace. So you want to make sure that you choose the one that doesn't talk about causation. Yeah. Cool. Yeah. So my vision is the stats one's going to have some that are like multiple choice that go with interpretation. And there might be some others that have like a calculation that you do. Or, you know, you pick the right number from the thing. So my theory is that the stats one is going to be more likely to be multiple choice, and the numerical method is more likely going to be numbers, but I can't be sure. Yeah, they've tested, yeah, I have no idea. It's the brand new land doing computer exams for courses like this. Cool. Okay, cool. I'm going to make one more attempt to talk about big O. On all I'm going to say, because people asked in this as well. All I'm going to say is, all I can say is how people seem to talk about big O. And it seems to me that when you do a Taylor polynomial sort of thing, and the error is big O of h squared, then that means that the Taylor polynomial of the thing and the Taylor polynomial of its error match up to, but not including the h squared spot. That's my understanding of it. Or when you do Taylor polynomials, Taylor's error formula, it's got an h squared in it, which would mean it's order h squared. That's my understanding of it. I don't know if I can get anything better than that. I'm sorry. But there are some early assignment questions in this course, like in the numerical methods bit, where you have to do like a Taylor polynomial calculation, and then it says show that it's order h4, and you look at it and you go, mine's only h3, and then it turns out that when you did the next Taylor series approximation, like you go to the fifth one, things cancelled out and you ended up with not an h3 in it. I don't know if anyone had a similar experience in some of the assignments in this course. Yeah. But that's it. Like that's all I can say is like if you show the approximation is order h cubed, then I would expect to do like, you've got f1 and f2, 1 dash and all this crap, and they've got Taylor polynomials. And then when you combine them together, if there's a special way of combining them, then some of these cancel, maybe h4, and the h cubes cancel, and there's no h cubed, and then you've got something with h4. That means it's order h4. Something like that. Yeah. I know that's really vague, but I can't be any more precise than that. Either your direct Taylor's error formula has an h to the 4 in it, or you can do a direct Taylor's error formula that's got an h3 and an h4 in it, and the 3 disappears. I don't know. That's all I can say, and I don't have anything better than that, and I'm really sorry. In a few years' time, it'll be better. That doesn't help you, but if you come to in person in the Maths Learning Centre and look at the situations where they ask you about it, then we can figure out what to do in response. Yeah. Okay. The idea is, I think, that if h is a small number, then h to the 4 is smaller than h cubed, and so it's better as an approximation. So if you've got h is 0.1 and h to the 4 is 0.0001, and so that's a better approximation in terms of error than just 0.1. Yeah. Do you computer science as well? They don't look at small numbers, they look at big numbers, and so n to the 4 would be worse than n cubed because they're looking at large things. But we're looking at small things that are close to the middle. Yeah. So just in case you're doing both, I just wanted to point it out, because the computer science, that has confused my staff a lot, having students from 2 different courses that treat O in different ways in the same room at the same time. But that is the nature of the Maths Learning Centre, so we're okay with it. Okay, so don't forget, I'm just going to stop the recording.